Hello, and welcome to my Combinatorics final. Today we are going to talk about Ramsey's theory. Hopefully after watching this video you will understand something fantastic about advanced mathematics. To begin, we are going to discuss Frank Ramsey. In 1928, Frank Ramsey published his paper on a problem of formal logic, which ultimately became known as Ramsey's theorem. As we proceed, we will explore briefly on some of the results in Ramsey's theory which have been stated as a way to find order within a large set of disorder. One example of Ramsey's theorem for graphs states that in any large finitely colored complete graph, there must exist some monochromatic structure. The main example that we will focus on today is the pigeonhole principle, which directly relates to a variety of problems in Ramsey's theory. This principle states that if there are n items placed in m containers with n greater than m, then one container must hold more than one item. If we have 5 pigeons and 2 holes, it is promised that we will have at least 3 pigeons in one hole. As viewed in this example, you can move the pigeons and try to make this statement incorrect, but it will never happen. You will always end up with 3 pigeons in one hole. Feel free to take some time to try it for yourself. Now, let's use this same basic principle to prove the following problem. Show that if each number in the set of 1, 2, 3, 4, 5, 6, 7, 8, 9 is colored red or green, then there is bound to be a 3-term arithmetic progression in one color. Before we can begin, I think it is necessary to define arithmetic progression. An arithmetic progression is also known as an arithmetic sequence. This consists of a sequence such that the difference between the terms is constant. One such sequence that we will be viewing today is x plus y divided by 2, found using the midpoint formula, and y. So let's get to it. But before we do, please acknowledge a few necessary descriptions. We will start with the basic 8 pigeonholes and 9 pigeons. Placing each of the pigeons, otherwise known as numbers, in the first hole available, we will eventually come to a mild dilemma. Our number 9 does not have a hole, so we will have to place it in one of the other pigeonholes. For this sake, we'll just start back at the beginning. Now that we have all of our numbers in different colored holes, you can see an arithmetic sequence. Actually, there is a few. One such sequence is 2, 4, 6, 8, and we also have 3, 5, and 7. So now let's go back and look at only having 2 pigeonholes. Let's begin by coloring x and y red. If x plus y divided by 2 is red, then we are finished. So let's color x plus y divided by 2 green. Now let's consider the number 2x minus y. If this number is red, then we are done, as 2x minus y, x is an arithmetic progression with the difference of x minus y. So, let 2x minus y be green. Now consider 2y minus x. If 2y minus x is red, then we have x, y, 2y minus x as an arithmetic sequence with the difference of y minus x. So, let's let 2y minus x be green. If you will notice, by doing this, we have created an arithmetic sequence involving 1, 4, and 7, with the difference of 3 in between each of them. The notation for these numbers is going to be 2x minus y, x plus y divided by 2, 2y minus x. Thus, the problem is proved.